we know generally for continuous random variables, we said we can either use the PDF or the CDF. So let's say we wanted to use the PDF. So we know when we use the PDF to answer probability questions for continuous random variables, to find the probability lies in some interval, we just integrate the PDF over the interval. Because we know area under the PDF gives us probability and we can find that area through integration. Right? So we know you based upon PDF that area under PDF is probability. So if we integrate the PDF over an interval, we'll get the probability the continuous random variable lies inside it. So if I want to find probability x is greater than x is less than b using the PDF, so I'll just integrate the PDF over this interval. And recall this is what the PDF of a continuous random variable looks like. E minus 1 by 2 sigma square x minus mu square dx. Right, so this is what the PDF of a continuous random variable looks like. Here, just keep in mind, if I'm writing the sigma square inside the square root, so I'll write sigma square. If I'm writing it outside the square root, then I'll just write sigma. But now the issue over here happens is, so we know if we want to find the probability for this continuous random variable using its PDF, we'll just integrate the PDF. This is its PDF, right? This is essentially its PDF, right? This is fxx, right? So just integrate the PDF over this interval a to b. But what is the issue? The issue here is we cannot integrate this directly, right? We cannot integrate this directly. So that's the issue here. So we cannot integrate this directly, right? So see, we don't know what the integral of this is. This is e minus 1 by 2 sigma square x minus mu square, right? If this was just e minus, if you didn't have a square here, then it's still fine. You could have integrated it. We know what the integral of ex is, right? But this is a square here. How do we integrate this now? So the issue is that, right? So typically, yes, for continuous random variables, you will use a PDF to find its probabilities because you can integrate the PDF over the interval to find the relevant probability. But the issue happens is that we cannot integrate this type of, right? So we can't integrate the PDF directly. Okay, we have another option. Let's use the CDF instead. We can use the CDF as well. We discussed this in an earlier part where we said that if you can use the expression for the CDF, because remember the CDF is probability x is less than equal to x, and we can use this to find any other probability as well involving the continuous random. So if I want to find probability x is between a and b, I can write it as fxb minus fxa, right? This is how we could do it. But again, there's a but here. But the problem is that we find fxa and fxb through integration. How do we go from PDF to CDF? We go through integration. So we can still, the fact that we can't integrate the PDF means that we can't use the PDF directly to find probabilities by integrating it over the relevant interval. And then we can't also use the PDF to find a simple expression for the CDF in which you can then later plug in A and B, right? Because the way we go from PDF to CDF is through integration, right? So we go from PDF to CDF through integration, right? Like we know over here, if I had to find fx of x, this would just be the integral from minus infinity to x. 1 by 2 pi a sigma square, then this becomes e minus, we can just write y minus mu whole square divided by 2 sigma square d. Y is just a dummy variable here because we have x in the limits as well, right? So the way we would find the CDF is through integrating this PDF, right? Integrating the PDF, right? So the fact that we don't know, we can't directly integrate the PDF, we can't even find a closed form expression of the CDF, right? So for a normal random variable, we don't have a closed form. Because see, if we had a nice closed form expression of the CDF, once I had what fx is, then I could just plug in A here and I could plug it in B here and find their values and construct them. But the problem is that because we can't integrate the PDF directly, we can't find closed form expression for the CDF. So for a normal random variable, CDF does not exist in closed form. What we mean by this is it does not exist in closed form. What do we mean by this statement is no simple expression for CDF. Right? We don't have a simple expression for the CDF where I could just plug in A and I could plug in B, because to find this expression for CDF, we would need to integrate, and we can't integrate this PDF directly. No simple expression for CDF. Right? Like we have for exponential and uniform random variables, which are other common types of continuous random variables. Right? For them, like for exponential, for x greater than equal to 0, we have 1 minus e minus lambda x, right? This is fxx. right? We have this nice simple expression for the CDF. When you plug in any value of small x over here, then you'll get, like, for example, if I wanted, so from here I can see fxa is 1 minus e minus lambda a. I can find fxp as 1 minus e minus lambda b. But you don't have a simple expression like this for the CDF of a continuous random variable, because again, we can't integrate the PDF directly. So as a result of this, we cannot find a simple expression for the CDF. So typically, yes, when we find probabilities for continuous random variables, we can either use the PDF or CDF, but that does not work for normal random variable because we don't have, because we can't integrate its PDF directly. So that also means that we do not have a simple expression for CDF. So how do we get around this problem and find probabilities for continuous random variables? We use standard normal distribution tables. Now, there are different types of standard normal. There are different types of standard normal There are different standard normal distribution tables that exist, right? Which provide us slightly different, which provide us slightly different information related to the standard normal random variable. But the one that we're going to use is a table which gives the CDF values for the standard normal random variable. And remember, when we talk about standard normal random variable, we said we denote it by z and we denote its CDF by pi rather than t. So we have different standard normal distribution tables that help us answer probability questions for normal random variables. So the table that we'll use is the one that provides the CDF values for standard normal random variables. And we'll see how we can use this table to answer any probability questions for a standard normal random variable itself, and not just for that standard normal random variable, but that standard normal random variable table can answer probability questions for any general normal random variable, right? So we're going to basically, to answer probability questions for normal random variables, PDF and CDF won't work because we can't integrate the PDF directly. Instead, we're going to use a standard normal random variable table to answer probability questions for any normal random variable, regardless of whether it's standard or not, right? So the table that we have, it's going to give us probability values for the standard normal random variable, but we can use that to answer probability questions of not just a standard normal random variable, but any normal random variable in general, which we'll see later.